Hello, our topic is image colorization. We are group 98 and I'm Ajay. So the colorization of images can not only enhance our understanding of the past, but can also ensure that historical events do not seem like they were farther away than they really were. And with the 1960s civil rights era, for example, many teachers agree that it's important for students to understand the events of history were fairly recent history, and constantly viewing this era in black and white may not give students a complete picture. So that's our motivation for choosing this topic. So the task of colorization has been done manually and painstakingly throughout history, and we want to explore how we could automate that process through the use of machine learning and neural networks. So that's our focus for this project. Our data consists of 25,000 grayscale images, and the color information, or the A and B channel information, is in separate files. And all the files are NumPy files for more efficient storage, and the Kaggle data we are using has been refactored specifically for the task of image colorization. So the input here would be the grayscale image on the left, and we can train our model based on the color information in the A and B files that are also visualized here for each image. So the A and B channels are used to make what is called a lab image. The lab image is nothing but the grayscale image with the A and B channels stacked on top of it, and that's the lab image in the middle. And from this lab image, we can then convert to the fully colorized image using the Python CV2 library. And we are using lab color space because it's less complex to deal with than the RGB color space, which provides three channels. With the lab color space, you can only predict two values.
Hi everyone, I'm Deepak. Our baseline model is simple unit, which is a CNN encoder decoder model. We took a grayscale image from lab space as an input, and the model learns to predict the AB color channels. The output is simply combined with the input L and converted back to RGB with OpenCV. We have trained this model with L1 loss and Adam optimizer at a learning rate of 0.003 for 5 epochs with the batches of 16. Um, then we move to the final model, which is an encoder, which is in GAN. We have used residual unit as a generator and pair it with the CNN critic. Making it a convolutional Wasserstein GAN model. The generator still receives the L as an input, but it's now trained adversely to produce AB channels that fool the critic. The discriminator still receives both real and generated images with the LAB images, learns to score them using the Wasserstein distance. Uh, this is the final architecture you can see over here. The generator is a residual unit, which means encoder and decoder stages includes residual blocks for better gradient flow and detail retention. The critic is simple file in and with instant normalization and leak array loop, designed to stabilize training under the Sartin GAN framework. Unlike traditional GANs, we don't use sigmoid at the end. Sartin GAN relies on real valued outputs for better convergence. Um, these are some optimizations up that we have took the generator is trained with the two losses of a certain loss to improve the realism and L1 loss to increase ensure the accuracy in the color reconstruction. We have used Adam and custom beta values and clipped the critic weights between point minus zero point 0.01 to 0.01 to enforce the Lipschitz condition. The critic is trained 5x more frequently than the generator to provide stronger feedback. We can see the results in the evaluation metrics. Now, this is the inference of the baseline model that we had. You can see the color is somewhat reasonable, but still lacks the texture, fidelity, and realism, especially in tricky regions like the shadows or the textured background. Whereas if you see the final model outputs, here is the resonant hue, the Saturn gain output. Compared to the baseline, it produces sharper edges, more vibrant colors, and capture more subtle textures far better. This reflects the strength of combining adversarial learning with residual enhancements. This is an external image that we have ran the test. When tested on external grayscale, which is from Unsplash website, the baseline again struggle with the realism, but the colors feel washed out. Um, whereas, the resonant Saturn GAN model performed very well, visually appealing and elastic coloration. This shows the model's generalization ability even on unseen images out of the training data.
So for evaluation, we use SSIM, LPIPS, and FID metrics. They basically compare images with each other to see how similar they are. So this is a result for baseline model that we implemented. And this is the final, like the result for the final model that we implemented. As you can see, we got a significant boost compared to the baseline results. So we don't have any prior experience with working with this topic, but we have worked before with image-related topics like classification and segmentations. And so these are some of the challenges that we faced during our project. So basically, there was some unstable GAN training. We also lost few fine details, some color bleeding and oversaturation. We also had some difficulty in evaluating realism. But in conclusion, our project performed better than the baseline model that we implemented. Thank you.
Yeah, in conclusion, we are looking forward to have the diffusion model, but due to time constraints and training constraints, we cannot do that. But diffusion might be a better use case than this. Thank you.